So last time we just introduced single particle potential in a single electron system in a box, and we play some mathematical trick, but it's not a trick, it's just a Dirac notation, nothing more. And imagine that we have the potential which influence that particle inside the box, and this, for example, the electron could get scattered by this potential. And before the scattering, the electron is in the state, say alpha prime, but after the scattering, it becomes alpha double prime, for example. Okay, and we could rewrite this potential operator in quantum mechanics in terms of sort of a creation and destruction operator, which we will introduce in just a moment. But let me just remind you, in the last part of the last lecture, which is using the Dirac-Broglie-Castet to rewrite this potential operator in terms of matrix element, here V alpha prime alpha double prime times this kind of operator, which is n by n matrix. And this n by n matrix, when we operate this onto any arbitrary, say, Dirac-Castet, it gives us either alpha prime if alpha is the same as alpha double prime, or 0 if they are not the same. Okay, so this is nothing but orthonormal condition in quantum mechanics. But we have a different kind of interpretation from the ordinary quantum mechanics. What we can interpret is that this operator, when acting on this state alpha, is going to destroy this alpha double prime, but create a new state called alpha prime. Okay, so that's U yesterday, okay, which is the old U, which I call this alpha double prime, and alpha prime is a brand new person when you wake up in the morning. Okay, that's the new you today. So, in a sense, all of us actually destroyed our old selves, living in the time of yesterday, and we are a newborn person when we wake up in the morning today. Okay, it's like our old self is dead, but there's a newborn person which comes from the old yourself, which is already dead, but you got a new life today. So in terms of this interpretation, we could simply just understand this single particle scattering as you destroy an electron state as an initial state or incoming state, but instead you create a new one after scattering. Okay, so that's really a straightforward interpretation, but it's completely new interpretation, because once we interpret this kind of operator in such a creation and destruction context, then we can really add or remove a particle as we like, because we can create a particle or we can destroy the particle, okay, simply by using this operator. So this is very convenient, very powerful, and that's the essence of a second quantization. So, but we need to take reference when we do the creation or destruction kind of processes. And the reference is the vacuum. So which I use this zeros castet to represent, it's kind of a single particle vacuum state where you don't have any particle there, just nothing. And in terms of many body system, this vacuum represents the ground state of a many particle system. Okay, so there's no excitations, since there's no quasi-particles. Okay, but vacuum does not necessarily mean there's empty or nothing. Okay, so kind of a philosophical concept. Many body system, for example, inside the Fermi sphere, you get fully occupied electrons, right? But there's no quasi-particle at zero temperature, and we can call this many particle ground state as vacuum, because there's no quasi-particle standing outside of the Fermi surface, and those occupied, states by electrons are really stable states. So it looks like there's no particle there, even if there are many particles. But to us, it's nothing. It's just empty. Because we are pretending that there's no particle, because there's no quasi-particles. However, it doesn't necessarily mean there's nothing. There are something, but these somethings are really stable states. So we can ignore the existence of them, right? So that's called vacuum. But here it's just a very simple idea that there's no particles in that vacuum state. And of course, the vacuum state is normalized to 1 if you simply just take the inner product and take the inner product. And of course, we could take advantage of such identity matrix in Dirac notations many, many times. And we could rewrite this kind of a creation destruction operator in a different way, because this is nothing but 1. And we insert 1 as a number or as a unit matrix anytime, anywhere we want. We can insert it here and there and in the middle, whatever you like it, right? But here we particularly choose, the in between this branch and catch states to insert such a vacuum normalization condition. But as I mentioned before, we could look at this object this way in terms of the blue circle, but we can also look at this operator in terms of the orange circles, right? So if I look at this in terms of this orange part and that orange part, and each of this orange stuff has a new type of interpretation in quantum mechanics. Okay, so for example, if I take this object and we could actually borrow the interpretation that we did here by replacing this alpha double prime by the vacuum state, right? So this is the same type of operator, except now I simply just replace alpha double prime by the vacuum state. So we should interpret this operator in the same way that we interpret this alpha prime, alpha double prime operator, right? But how do we interpret this? Well, we say that we destroy the state alpha double prime and we create the state alpha prime. Likewise, if I replace alpha double prime by this vacuum, and I can interpret this as I destroyed a vacuum state, but I create alpha prime. So what does that mean? So you really create a particle out of vacuum, right? Suppose this is a vacuum, there's nothing, or there's something, but they're very stable, and we don't count them. Then all of a sudden, you destroy that state, but you create a particle there. So this is what this operator tells us, that I really create a single particle out of a vacuum ground state. So that is precisely this operator is telling us, and symbolically, we just borrow this quantum mechanical operator, and we call this C dagger alpha prime. So this refers to the Hermitian conjugate in terms of the matrix representation of a quantum mechanical operator, which we will discuss that later. So physically, we simply just interpret this as creation of a single particle in the sense of a quantum mechanical operator. And this is represented in a shorthand notation, C dagger alpha prime, where C refers to the conduction electron, or we don't specify what particles it is, but imagine that these are electrons, and we call this creation of a single electron state, C dagger alpha prime. Okay? So likewise, for the other orange parts, again, we use the same interpretation to define the destruction of a single particle state by saying that this operator destroys a single particle state, which I call this alpha double prime, and create a state which is nothing, which is empty state. I destroyed a single particle state and I create an empty state. What does that mean? This means I really destroyed a single particle, right? So then we use conjugate notation to the C dagger alpha prime, and we denote this process as a C alpha double prime, where C refers to annihilation operator or destruction operator, and of course alpha double prime refers to the states that the particle occupies to be destroyed. All right. So you can see that the operation of creation and destruction are really opposite or conjugate to each other. Okay, just like a complex conjugation in quantum mechanics, and therefore in an operator sense, this is actually the Hermitian conjugate of that, or this C dagger is actually Hermitian conjugate of C. So we have such a relation, right? So C dagger is actually the Hermitian conjugate of C. So in terms of the matrix operation, the C dagger matrix refers to you interchange the matrix element I and J for this, and then you put the Hermitian complex conjugate to all the matrix elements. So that's the sort of a conjugate operation. So this kind of notation can also represent kind of a particle-antiparticle relation, right? Suppose I create an electron, which means that I destroyed a hole, and to create a hole, I mean I destroyed an electron, right? Okay. So this is sort of a particle-hole conjugation between C and C dagger. To represent a hole, we simply just destroy an electron, and that's the way we create a hole. To create an electron, of course, we should destroy the hole, vice versa. So electron-hole pair is actually this kind of C dagger and C operation. So now we could rewrite this potential operator for a single electron scattering in terms of the matrix element V alpha prime alpha double prime multiplied by simply C dagger and C. Because C dagger is this and C is that, okay? So this is very simple to interpret, and this is the correct way to understand the single particle scattering because, as I mentioned, when you have a single particle scattering, you should destroy your incoming state, and then you should create an outgoing state. And this is precisely what happened here. First, we should destroy the state alpha double prime as the initial state or incoming state, and then we should create an outgoing state, which I call this alpha prime. Okay? So I kill this, and I create that. How do I know that I create the particle? Because there's a dagger here. How do I know that I destroy the particle? Because there's no dagger here. All right? And so it's very easy and simple to interpret the single particle scattering in terms of initial and final state, so that we destroy the initial state and we create the final state. Okay, so you could look at our textbook, Flansburgh, or David Pines or Kittel's. These notations are everywhere, so you could check very easily. So now we should apply this notation for, say, a single electron in a box. Now, inside the box, there's no potential, and there should be only kinetic energy. So let's just apply this to kinetic energy of a single electron in a box. Remember, the kinetic energy in quantum mechanics for a single particle is nothing but p squared over 2m, where p is a quantum mechanical operator, and representing this kind of a minus RH bar d by dx acting on this wave function. But we could also use this Dirac notation to represent this electron state in momentum space. So if I use the same notation or convention for a single particle potential, and I could just rewrite this in terms of this matrix element, the creation and destruction operator. Suppose that the alpha and alpha prime or alpha double prime is simply just the momentum states. There's no scattering. I can only count the particle. And then this is simply just single summation over momentum variable p. And this is simply just what? P and p squared and p c dagger p and cp. So later we'll come back to this, but let me just finish this algebra. So this, in terms of a single particle quantum mechanics, when momentum operator acting on the momentum space, and this gives us the momentum p as an eigenvalue or p squared, and multiplied by the orthogonal normalization condition for p Bros and p cascade, and this is nothing but 1. So I simply just erase the remaining part by reporting their eigenvalues. So this is nothing but sum over p squared, c dagger. All right, so later we will define this operator as the number operator, which records the number of the particle. So, but let me just try to interpret this, c dagger p and cp. So what do I mean by this operation, c dagger p and cp? This is actually two-step processes. So there are two operators. One is the destruction operator, and followed by the creation operator. Okay, so what I mean is that I should first destroy a single particle state at p, and then I will create the same state p again. So what does that mean? Suppose there is a state called p, and if I operate this c dagger c on this state p, what I really do is actually I first destroy that state p, and then the state becomes a vacuum, right? So if I perform this first operation, and then I should create a new particle, but this new particle is actually the same as the old particle carrying momentum p, by creating operation c dagger p. So what do I really mean by this kind of a redundant or stupid operation? This means that we count the particle number. What do I mean by this? Suppose there's object called chalk, right? Okay, and there's just single one object here. How do I know that there's just one particle here, like this? Well, first I should destroy this, and this disappeared. And then I will, recreate the same thing. So if I destroy the state and I create the same state once, I know there's one particle ever lived, right, before. So therefore, this operation is actually count the particle number. So we will come back to this interpretation just a moment. But this is the complete story of a single particle quantum mechanics in terms of the second quantization formalism. So in terms of potential, we destroy the incoming state and create the outgoing state. In terms of kinetic energy, we simply just count how many particles are there, and then we multiply the particle number by the kinetic energy for each individual particle. Okay, so this is the total kinetic energy. Right? So this is the particle number, but this is the kinetic energy per particle. And therefore, the whole thing represents the total kinetic energy, which is the kinetic energy per particle multiplied by the number of particles. Sounds simple and easy, right? So let's take a short break. When we come back, we will generalize this idea to a many particle system, but we use again this the single particle state as a basis, and to construct the many body wave function. Okay, so let's generalize this to a many body system, because we know that the solid state system is actually a many body system. There are 10 to the 23rd that many atoms, electrons. So we should deal with this many particle system, but we can take advantage of a single particle quantum mechanics in terms of the second quantization formalism, but let's just try to review this many particle system in quantum mechanics. We know that all the particles can be divided into two groups. They are fermions or bosons, right? Fermions satisfies Fermi-Dirac distribution, and bosons Bose-Einstein distribution at finite temperature. So, but in terms of wave function, and there are many particles, and each particle occupies different spatial locations and also carrying some quantum number, mu, which could be spin or angular momentum or whatever. And there are so many. And the total wave function of many particle systems is related to the product of the single particle wave function. Okay? So, and we know very well that suppose this is a boson. The boson wave functions are totally symmetric in space, and therefore, if I interchange the position of the two boson particles, and the total wave function is still the same. Meaning, if I have only two bosons and I interchange this, and I should get exactly the same product as a two boson system. So psi Ri times psi Rj is actually the same as psi Rj times psi Ri. That's for bosons. However, if they are fermions, then you know very well the Pauli principle tells us that if I interchange two fermions, their positions, I get extra minus sign, right? So this is phi of Ri, phi of Rj. It's actually minus phi of Rj, phi of Ri, if they are fermions. So the extra minus sign refers to the fermionic nature of a two fermion wave function. So likewise, in a many body system, we can have a many boson or many fermion system, and the total wave function in terms of the product of the single particle wave function either shows symmetric or anti-symmetric properties. They are bosons, they should be symmetric, and if they're fermions, they should be anti-symmetric. And so we could use this symmetric or anti-symmetric properties of boson fermions to construct the non-interacting bosonic many-body wave function, which is simply just a product of all the single boson wave functions. Okay, suppose there are n bosons, and each bosons can be described by the single boson wave function, u carrying quantum number nu1 and at position r1, and so on and so forth. So the total bosonic many body wave function is nothing but the simple product of this single particle wave function for bosons, and they are the same if we simply interchange any two of them. There's no difference, if I simply just exchange any two single particle wave functions in the product of this total wave function. But for fermions, it's a bit complicated because of this anti-symmetric nature, and in terms of this many particle, many fermion system, this total wave function is nothing but the determinant of this matrix. Because in the determinant, we get a minus sign for every permutation between any two fermion wave functions. So this is, say, nu1, r1. Okay, so this is simply just a determinant of this n by n matrix. So that, I think you should know from your quantum mechanics, right? And the prefactor is normalization square root of n factorial. And symbolically, we could simply just use kind of a symmetrized notation for bosons and anti-symmetrized notation for fermions. So if I write this way, so bosons, I simply just don't care about this orderings of those single particle operators, but for fermions, I should anti-symmetrize, and this S plus and S minus refers to the symmetrized and anti-symmetrized notation operator. And for this S plus, I do nothing, but for S minus, this refers to simply just determinant of this n by n matrix. So I simply simplify my notation by using this S minus operator for this anti-symmetrization of this many fermion wave function. And these two type of many particle wave function in terms of the product of the single particle wave function is called the basis. Okay, so they are called the basis. The basis state. So I could use a single notation for this kind of a basis state. Phi as a function of alpha 1, alpha 2, where alpha 1 could be this quantum number, say, nu 1, and also the position R1, and so on and so forth. This is called the basis of this n single particle state. Many particle states is actually a linear combinations of this basis function or basis state, which in terms of this kind of a Fourier decomposition, we get coefficient, which I call this C alpha 1 to alpha n, and then we sum over those alpha 1 to alpha n, but we should multiply this basis. In the many-body system, we can construct the arbitrary many-particle wave function, but this arbitrary many-particle wave function is nothing but the linear combinations of this basis function, and this basis function is either symmetric for bosons or antisymmetric for fermions. In other words, so these simple-minded product states serve as a basis function to be expanded when we construct any arbitrary many-particle wave function. It's like an eigenstate, okay, of a many-particle system. But this is the general formulation of this many-particle system. It doesn't tell us how to really find this out, right? So how do I really construct such a linear combinations? It's easier said than done. So such a general formalism is not very useful. So in particular, if we like to follow the particle, so there are two approaches which I should list it here. The first approach is follow the particle, and this is precisely this equation. It's telling us, remember, those basis function is actually a function of all individual positions, right? Suppose we know their quantum number and we know their wave function distributions in real space, and we should know this, arbitrary many-particle wave function. Okay. In other words, the first step is actually the ideal kind of a step that we can imagine from the single particle quantum mechanics, that we could really describe a Schrödinger wave function of a single particle in real space. And this is the generalization of a single particle Schrödinger picture, that we could follow the particle and to find them in real space. But this is simply just a wishful thinking. You know what wishful thinking is? Well, I hope I could really fly to the moon. So this is the dream that cannot come true. It's called wishful thinking. So this strategy, by following the single electron wave function out of a many-particle system, is a wishful thinking. This cannot be done because, if I try to follow this path, then I should know each individual Schrödinger wave function by solving 10 to the 23rd that many atoms in terms of Schrödinger equations. So it is impossible. This is mission impossible. Even though in general we know, suppose we know each individual Schrödinger wave function, and then we simply just, make the basis function and take a linear combination. Well, you do it. Everyone knows this can be done in general, in principle, but in practice, it cannot be done. It is, as I mentioned, mission impossible. You cannot solve that many Schrödinger equations simultaneously and self-consistently. And therefore, we should take the second path, which is precisely what we are promoting, which is we count the particle number. So how do we count the particle number? Well, the same basis function. Remember that alpha 1, alpha n, but you also like to know their real space distribution. The same basis function could be equally described in terms of occupation number basis. So in terms of occupation basis. So let me just explain this. So the same set of many particle states, but I cannot solve them in real space. Nevertheless, I can count them in sort of an occupation number basis, which means that I can count how many particles there to occupy the state alpha 1 and how many particles are there for this alpha 2 state. I don't know where they are. I don't care. Okay, but I do care is this kind of a distribution in number particles occupying a specific quantum state. So this alpha 1 could be in terms of a spin state or angular momentum states or momentum states or whatever. So you just find any normalized eigenstates you feel like convenient, and then you simply just count how many particles are there staying this alpha 1, alpha 2, and alpha n. So after exhausting all the possibilities, you can describe equally well this many particle system, even though you don't know exactly where they are, but you can count them. And we call this occupation number basis, n alpha 1, n alpha 2, and alpha n. Okay, where n refers to the number of the particle occupying the state alpha 1 for n alpha 1 and so on and so forth. Okay, so this is a different type of statistics or the counting method. So you can count them by following the particles, but you can also count them by the states that they occupied. And we don't have time to prove this equivalence between these two, but you could check our references. So I think we could take a short break, and when we come back, we will continue using this occupation number basis to rewrite this many particle wave function in terms of creation and destruction operator in terms of the occupation number basis. Okay, so let's take a short break. Let's continue. We could take advantage of such occupation number basis to try to count the particle number. So we have this occupation number, and we could just use the shorthand notation for the collection of occupation in many body state. And we could really construct the equivalent way of describing arbitrary, many particle states in terms of this occupation number basis, and this is nothing but the linear combinations of this occupation number states, right? So suppose this Dirac cat state n alpha 1 to n alpha n represents the occupation number in our occupation number basis the many particle basis function, then we can simply just perform the linear combinations of this occupation number states, and we can form the arbitrary many particle wave function. So this is what we call the second pass, which we count the particle number. And this description is actually identical to the first approach, where we try to solve the single particle Schrödinger equation for many body system, which is mission possible, but in principle we are able to write down such a general formalism, although this formalism is not very useful, but in principle we could still express this arbitrary many particle wave, wave function in terms of such a real space symmetrized, anti-symmetrized single particle wave function as a product, and we linear superimpose such a basis function, and we can form arbitrary state. But in principle, these two descriptions are identical and should be equivalent. And of course, we don't have time to prove that they are indeed identical. Instead, we simply just, most of the time, we just focus on this, but we simply don't follow the particle. And we should try to learn how to count the particle number, and therefore we should really focus on the first line here. But if we are able to find this kind of single particle eigenstate, and in principle we are able to find out this kind of a basis function, and in particular, suppose we are talking about the fermion and this anti-symmetrized wave function. Suppose that we know where they are and their quantum number, so we can actually use the same definition for destroying and creating a single electron, and to actually construct this basis function for, say, many fermions. And we could simply just define such a basis function like this. Suppose there are m particles or m electrons, and we can consider this collection of m electron states as the creation of a single electron n times, right? So you create out of a vacuum a single electron at state alpha n till alpha 1. You create n times, but each time when you create a single electron, you attach the different quantum number to that electron state. So, and in principle, we could do that. We can also count the particle number in real space. Of course, we could do that. So that is in principle durable. So we will come back to this counting later. But let me just write down the sort of mathematical identities describing such a occupation number basis, namely the completeness, also normal completeness, and this is also satisfied. And what does it tell us, right? So the occupation number basis is defined by those quantum number, which is nothing but the occupation number. It's a collection of bunch numbers, and each number tells us the number of particles which stay in a particular state, nu 1 or nu n, and they satisfy this completeness, and all this, just like the state alpha is actually a complete eigenstate. And when you sum over all the occupation number from 1 to, say, infinity, or up to right, and you get the total number stay fixed. So if you sum over all this occupation number, this number is nothing but the total number of the particles, right? So I can simply just it's like out of 100 balls, I could classify all those balls in terms of how many red balls and how many blue balls are there, and so on and so forth. I classify them in terms of their colors. But when I add up all these different numbers corresponding to different colors, and I should get back to the total number of balls, right? So that's the conservation of particle. So then this new state could be this principal quantum number, the spin and orbital angular momentum, and this m as a angular momentum quantum number, and so on and so forth. And suppose I could also define my vacuum of a many particle system. What I mean is that all the different quantum numbers, there's no occupation. There's nothing in state nu 1 and up to state nu n. So all the states, all the eigenstates are completely empty. So I could define this my many particle vacuum state. 0, and then if I could define my occupation number operator, nuj, wearing a hat, meaning this is the occupation number operator. If I operate this operator onto this any occupation number states, I get the eigenvalue equation where the eigenvalue is nothing but the occupation number nuj and multiplied by the nuj state. So this is how we count the particle number. So we define this occupation number operator, and we could access onto the any occupation number states, and the eigenvalues should be the number of this occupation number, or number of particles staying in that nu j state, and multiplied by this nu j state itself. So this is how we count the particle, and later we will define what this n nu j hat is. Okay, so it's called occupation number operator. All right, so this is I should say this mathematical identities to well define such a occupation number basis. So now it's time to formally define the fermion destruction operator and creation operator in many fermion system. Okay, so that's the fermion creation and destruction operator in many particle system. Okay, so far any questions? No? So you could read the first, say, chapter 1 or chapter 2 of Flansburgh. So there are some notations and descriptions of this occupation number basis there. So let's define this destruction operator, or I should say annihilation operator, Cp, as you sum over all occupation number. So the definition follows exactly the same way that we define a single particle creation destruction operator, but in a bit complicated way, because now there's not only one electron there, but there are many electrons, and they satisfy this kind of antisymmetric nature of the fermion wave functions. But suppose we have n electron states, and they are described by this occupation number, and we use all this bunch of numbers to label the occupation of each of the states that this electron occupied, and I should destroy an electron occupying state P, but there are so many, right? So from n1 to nn, and passing by ni, I sum over all such occupation numbers states, and I is not equal to P, and you could define such a destruction like this. Again, this Dirac-Bragg state is my initial state, as I mentioned. We should destroy the initial state. But what is the initial state? Well, there is a single particle there, and p equals to 1 initially, and I should destroy this. And as a final state, where this quantum number is actually p, there's nothing. Okay. So originally there is electrons in state p, but the final state there's no such a thing. So this electron state is gone. So occupation number is 0. So it is very clear definition that we destroyed a single electron state, because before we destroy, there was one, but after this operation, there's no one. Okay, so it's really well-defined operation, but there is some complicated, this anti-symmetric nature of a fermionic wave function. So there is a non-trivial, -1 to some power involving in this kind of destruction of a single electron out of many electrons, because there are many electrons. If you would like to destroy that electron, you need to first go to that state and kill it. But there are many electrons before that electron state p, so you need to passing by all the remaining electrons one by one. But when you pass by all those electron wave functions, you need to interchange the wave functions, right? So that you get many permutations of your many fermion wave functions. Once you exchange two wave functions of fermions, and then you get minus 1. And that's how you get this -1 to the power of mp, where mp is the total number of occupation starting from the first state to p-1 state. So you should really exchange your wave functions with all the states before that electron state that you want to kill, right? So it's like you have many obstacles, right? So this is state p, but this is state 1 and state 2 and state p-1. So this is you, and what you want to do is you want to kill that guy. I want to kill it. But I don't want to kill all the other electrons. Of course, there are many other electrons, p+1 to the very end. I only want to kill this guy. But what do I do? Quantum mechanically, you need to go past the first electron, and then past the second electron, the third and fourth, and so on and so forth, and so on and so forth, until past p-1 electron, and then you already close to state p, and then you kill it. Okay? Good. But of course, when you pass by all these electron states, you are also an electron state, or electron destruction operator made of electron wave function, and so on. So you are an electron, and you want to pass by that many electrons, and which means that when you pass by, you exchange your position with the other fermion wave functions. So there is one factor -1 when we exchange your wave function with the state 1, and suppose there's another electron in state 2, then you exchange that state with your wave function, and you get another -1, and so on and so forth. Of course, not all the states are occupied. Suppose this is the empty state. There's no electrons, and you simply just pass by without exchanging your wave function. There's nothing to exchange if there's no electron occupying the state. So for empty state, you simply just go through. But if there is an electron here and there and there and there, and you need to exchange. and therefore you need to really count how many electrons are there before the state P. Okay? So this is the logic. This is why you need to be careful with the -1, because they are fermions or electrons, and when you exchange to fermion wave function, you get minus sign. And this is the factor of -1 that you should experience when you really want to kill that guy at state P. And this summation is simply a bunch of 1 and zeros. So this is 1 plus 1 plus 0 plus 0 plus 1 plus 0 plus whatever. Okay? So some of the states are empty, but some of the states are occupied. So you simply just count how many are there, and you get the number. And this is the exponent that you need to put here. Keep track of this fermion, antisymmetric properties of fermions. So let's take a short break. When we come back, we will check this definition and this consequence of this definition. When we really operate this kind of a destruction operator in a many electron system, and what they would lead to. So let's check the fermion properties of this CP. So first of all, the CP, if you act on empty states for state P, you get nothing. And if you destroy the single occupied state in P, you get this as we defined. But if you destroyed this fermion state twice, you get nothing. So let me remind you so-called the occupation number for fermions in many particle system. Okay, so the Pauli principle tells us that no two electrons carrying the same quantum number can actually stay in the same state, right? So therefore, for any arbitrary fermion systems, there are only two occupation possibles. One is 0, another is singly occupied. Okay, so this is empty, and this is singly occupied state. So that's the first thing. Of course, for bosons, you could have as many states as possible. Staying in the same ground state. We call it Bose condensation, and we will talk about that later. But let's just focus on the fermions, where they can only have this 0 as occupation or 1 as occupation, but nothing else. So suppose there's nothing in state P in the beginning, and you want to destroy a nothing, and of course you'll get 0. Okay, so 0 is a value, mathematical value, which is in general is not the same as the vacuum state. 0 times anything is 0, but the vacuum state is a vacuum state where there's no particle staying there. Okay, so 0 is not identical to the state 0. Okay, so this is really important. So if there's no particle there, you cannot destroy this particle anymore. So if I use a notation, I should really use a cross representing that this is not allowed, because you are at the ground floor and there's no basement for you to go downstairs. So there's nothing below this ground floor. So if you like to actually go to the lower floor, you'll get lost. But if there is one particle here and you like to destroy this, that's really good, because this is a single particle and you could kill this, of course. And when you kill this, you get empty state. The empty state is not 0 state. It's a 0 state, but it's not 0. Okay? It's just that this state is empty. The empty state is a quantum state. It's not the same as the value 0, so that's the one thing. And of course, you cannot destroy a single electron twice, because if you destroy a single electron twice, and of course you'll get to the basement, but you are not allowed to do so. Okay, so Cp squared acting on any states of fermions is actually 0. And so that's just the properties of the destruction of a single electron out of the many electron state. So let's just define this creation operator. Okay, so the creation operator is defined in the same way as the destruction operator, which is in the opposite direction, because now you would like to increase the particle number by 1. So the initial state and the final state is actually reversed with respect to the destruction operator. But the logic is just actually the same. So you want to create a single electron, so you must come from the initial state where there's no electron there. So this is your initial state where the state P is empty, and then you create a final state where there is a 1 electron there. Of course, you need to take care of the prefactor minus 1 to the power of mp, where this mp is defined the same way as before. So now let's check the algebra. The C dagger P acting on the empty states of state P, which is this as a final state, just like this. And if there is already 1 electron occupying state P, and you want to actually increase the particle number by 1, but by Pauli principle, it is not allowed because you cannot increase the particle number by 1 if there is already a 1 particle there. Okay, so let me use this Hilbert space one more time. So this is state 1 and state 0. You would like to go 1 floor up, you must come from the ground floor, and then you take the elevator to the first floor, the second floor. And if I'd like to go to the third floor, there's no third floor. Okay? And of course, you cannot create electron in the same states twice for the same reason. Because, there's only 2 possible occupations for fermions, 0 or 1. And so this is, 0 if you apply C dagger twice. So see, this kind of properties are really identical, but in the complementary way that, you cannot create 2 electrons for the same states. You cannot destroy the 2 electrons. Okay, and so on and so forth. There are only 2 floors, the ground floor and the second floor. Nothing else. No basement, no third floor, nothing. So now let's check the this commutation relations. Remember the fermion wave function. When you exchange any 2 fermion wave functions, you got minus sign. And these properties will actually show up here in the second quantization formalism. So we have this psi mu j, psi mu k. It's actually, and in terms of Schrödinger wave functions, I can actually use the Schrödinger wave function, say psi star mu j, to represent such a say single fermion wave functions out of n fermion wave functions. Of course, I cannot solve for them, but in principle, I can imagine that there are such fermion wave functions. And when we exchange these 2 particles, I get minus sign. Okay, so that's from the quantum mechanics. But I could rewrite this exchange properties in terms of the second quantization formalism. So we will check this property in just a moment. So I could create 2 electrons, and I can exchange them But when I exchange these two C daggers, I get a minus sign here. So this minus sign is actually the same minus sign in the Schrödinger wave function. So there is a one-to-one correspondence between the second quantization formalism, the exchange of these two operators, Fermi operators, and this exchange of two wave functions. So, but if you could just rewrite this, what do you see? Okay, so this is C dagger nu j, C dagger nu k plus C dagger nu k, C dagger nu j, actually 0. Okay, so in this second quantization formalism, this is what we call this anti-commutation relation. So I put this C dagger nu j and C dagger nu k together inside the brackets, and I put the comments in between. And this is the operator in quantum mechanics, and the definition of the operator is that the A times B plus B times A. Okay, suppose this is A and B. So I think everyone should be familiar with in quantum mechanics. So if I put this in the anti-commutator, this is AB plus BA. But what about the other combination? So if I use another bracket, A and B, this is called commutator, AB minus BA. So the commutator relations describe the bosons, but the anti-commutation relations described the fermions. So this equation is just one of the three anti-commutation relations for fermions, and we could define such an anti-commutator for two fermion operators, and we can check whether this definition of C P and C dagger P over there satisfy this expectation of anti-commutation rules for exchanging two fermion operators. So let's check the anti-commutation rules. So let me just write this very quickly. So I have this C nu I, C nu j, anti-commute, and also C dagger nu I and C dagger nu j, anti-commute. But I have a slightly different anti-commutation rules for one destruction and one creation. So this is eta nu I and nu j, which is 1 if nu I is nu j, and 0 if nu I is not the same as nu j. So, but before that, let's just check this first. Okay, so check C nu I, C nu j, acting on any states, and nu I equals 1, and nu j equals 1. So let's just do the operation, right? So first, we should kill nu j states, right? Okay, so this is given by -1 to n nu j, which is sum of all the occupation number before this nu j state, right? So after the first operation, I get this, and nu I is 1, but n nu j is actually 0. So then I should kill the second electron, but when I express the state like this, say I should take this order seriously because nu I is placed on the left side of nu j. So when nu j changes occupation, the second operation doesn't do anything to this nu j state, and we don't care about this change of occupation when we actually perform the second operation, because the second operation is the operation where we kill the state nu I, but nu I is actually on the left side of nu j. So when we calculate this -1 to some power, it doesn't matter what this value nu j is. I don't care about this. So I get -1 to the power of nu j times another -1 to the power of nu I, and then I kill the second guy. Right? Okay, so that's my first calculation, the first order. So the second operation is that I exchange the order of these two operators. So I first kill this nu I state and then nu j state later. So, but my initial state is the same. So let's kill the first guy. So the first guy is this. So I get -1 power of nu I and c nu j. Nu I is actually 0, and nu j is actually 1. Remember, now nu I changes number from 1 to 0, so it will affect my second operation, because when I kill this nu j, I should really care about all the occupation number on the left side of the nu j, which includes nu I. But nu I changes value from 1 to 0, so this will give me a slightly different exponents for the second operation. So this is -1 to what? Nu j minus 1. Remember, now a particle is gone already, but you need to count that particle number at the second operation, and therefore I don't care what values nu j is, but at the end it should be one particle less. And then I simply just copy this after the second operation. So you can see that you simply just count the -1 factor. So the first operation, you get -1 to the power of what? Nu j plus nu I, right? So this is nu I plus nu j. But what about the second operation? So this gives us nu I plus nu j minus 1. You see that? So they differ by a minus sign. So I don't care what this capital Nu I or capital Nu J is, but I do, the only thing I know is that they are different by a minus sign. Okay, I don't need to know, how many occupation or how many particles are there before, the electron that I want to kill. I don't really need to know. The only thing I need to know is that they are different by a minus sign, and they differ by a factor of -1. So therefore, if I just add these two, C nu I, C nu J plus C nu J, C nu I, acting on my initial state, I got 0 because they differ by a minus sign. So then I prove the first set of anti-commutation rules. This is checked. Here comes your homework. Time is up. Exactly that's what I need to stop here. Check the others. Okay, C dagger I, C dagger J, it's actually 0, and also Ci and Cj dagger, it's actually delta Ij. Okay, so check this one and this one. So you can use any arbitrary states you like as your initial state. So it doesn't matter where you start from, 1, 1 or 0, 1 or 1, 0 or 0, 0. It doesn't matter. But let's just do this. You actually exhaust all these possible initial states. You do it 1, 1, and 1, 0, and 0, 1, and 0, 0. So use the 4 initial states to check this. Okay? So you will convince yourself that it doesn't matter what the states that you use to do this operation. These identities are always satisfied. So it's time to stop, and I hope you enjoy this homework. This is a very important, interesting exercise for you to get familiarized with the creation and destruction operators in many fermion states.